Hello everyone, welcome to my channel. This channel is focused on educational matters, and we particularly look at things that you may not have ever heard of before, but that could enrich your life if you did. And today is video number 187 on the reciprocal system of theory. And this is a theory from Dewey B. Larson, who died back in 1990, but before that he had written many books on his reciprocal system. The basic idea is that we live in a universe of motion. The universe is not made out of matter, it's not made out of energy, but it's made out of motion. Matter and energy are merely two different forms of motion, as are really all the different scientific quantities out there, such as pressure and acceleration and electric capacitance and electric charge and electric current and magnetic flux and viscosity and fluidity and all of these different properties of matter, but also properties of mechanics are forms of motion. And motion is the relationship between space and time. So all of those things can be expressed in a fraction that has either time or space as the numerator and either space or time as the denominator. Space or time both have their coordinate aspects, their three-dimensional aspects, x, y, z coordinates. So we recognize coordinate space, space being three-dimensional, but we don't always recognize that time also has its three-dimensional aspect, which Larson calls coordinate time. And then there is the clock aspect. We generally recognize that time follows a clock. It is always getting later and later and later, but in no particular direction, just later and later and later. And in the same way, space has its clock aspect. Clock space is the progression of space. Space is always getting farther and farther and farther apart, which was observed by the Hubble telescope, observing the distant galaxies all moving away from each other. And the further away they are, the faster they're moving away from each other, but in no particular direction. That is a scalar motion. And so that really sets up two separate sectors of the universe, especially when you throw in the discrete unit postulate, meaning that there is a minimum unit of time and a minimum unit of space. And there's no time less than a 1 unit, and there's no space less than 1 unit. And exactly 1 unit of space in 1 unit of time is the speed of light. So the speed of light is really the boundary, the midpoint or the null point, the origin, the ether of this universe. And there's half the universe that's moving slower than the speed of light, and half that's moving faster than the speed of light. The half that's moving slower than the speed of light is the half that we generally recognize. Larson calls that the material sector. This is where the scientists are making all their measurements and all their observations and all their hypotheses. And this is where Einstein is saying that the speed of light is the maximum speed of the universe. Well, he's talking about the material sector, that speed of light, which is actually the midpoint of the universe. But to the material sector, it appears as if it is the maximum speed. But once you cross that speed of light boundary and go into the sector of the universe that's moving faster than the speed of light, which Larson calls the cosmic sector, in that sector of the universe, the speed of light is actually the minimum speed of the universe. Everything's moving faster than the speed of light. Now, in the material sector, you have a setting of basically 3 dimensions of space, coordinate space, and clock time, progressing time, one-dimensionally. It's always getting later and later and later. That is what we recognize in the material sector. In the cosmic sector, the roles of time and space are reversed, are inverted. And so in the cosmic sector, we have 3 dimensions of time and 1 dimension of space, clock space. Space is always getting farther and farther and farther apart. And you have this coordinate time. So that's the generalized basics of the reciprocal system. He worked that out, and then he came up with these fundamental postulates, the first of which we just went through, and the second of which has primarily to do with mathematical relations and geometrical relations. And then he deduced a theoretical universe from that using kind of if-then deductive reasoning. And so he came up with a theoretical universe and then eventually compared it to the actual universe that the scientists had measured and observed over time. And basically, Larson's universe fell in practically seamlessly with the observed universe, other than in areas of the very small, the very large, and the very fast. The same kind of areas where the relativistic theory of Einstein's also filled in the gaps where Newtonian physics wasn't providing all of the answers. So it's kind of a replacement in a certain sense for relativity theory, and that's why Larson has a book that's actually called Beyond Newton. The Newtonian universe and Newtonian mechanics is basically correct when you're talking about, you know, the macro or the universe that we basically observe. But on the margins, in these areas of the very small, the very large, and the very fast, maybe in the very slow, that's where Newton's universe doesn't provide, Newton's equations, they don't provide the answers. Einstein's don't either. And so Larson kind of fits in right there. Not only does Larson's theory provide answers for those relativistic areas, but they also provide the same answers that Newtonian physics provides. So it's a full, comprehensive theory of everything. But not only that, but it penetrates into other areas, such as this faster than light realm called the cosmic sector, where we get phenomena such as intelligence and consciousness and life in general, and that goes way beyond where Newton was going. Okay, now we're looking at Larson's 1979 book here called Nothing But Motion, and we're into the beginning of chapter 13, which is called Physical Constants. I want to go back just a little bit in this paragraph, the last paragraph that we read, and then go forward from there. So he's talking about the fundamental constants of present day physics. And he's quoting an article from Science News. We must either, the article says, swallow them ad hoc. This is fundamental constants, without justification for their necessity, their constancy, or their values. Or we must accept the Machian hypothesis that they are, in some unknown way, determined by the contents of the universe as a whole. The development of the reciprocal system of theory has now resolved this dilemma in the same way that it handled a number of the long-standing problems considered in the earlier pages, that is, by exposing it as fictitious. When all quantities are expressed in the proper units, the units of space and time, the natural units of which the universe of motion is constructed, the fundamental constants reduce to unity and vanish. So they reduce to one and they vanish. A preliminary step that has to be taken before we can we can compare the mathematical results derived from the new theory with the numerical results or the numerical values obtained by measurement is to ascertain the conversion ratios by which the values in the natural system can be converted to the conventional system of units in which the measurements are reported. Inasmuch as the conventional units are arbitrary, there is no way in which the conversion factors can be calculated theoretically. It is necessary to utilize a measurement of some specific physical quantity for each independent conventional unit. Any physical quantity which involves the item in question and can be clearly identified will theoretically serve the purpose. But for maximum accuracy, certain basic phenomena that are relatively simple and have been carefully studied observationally are clearly preferable. There is no question as to where we should obtain the value of the natural unit of speed, or velocity. The speed of radiation, measured as the speed of light in a vacuum, 2.99793 times 10 to the 10th centimeters per second, is an accurately measured quantity that is definitely identified as the natural unit by the theoretical development. That is one unit of time, 1 unit of space over 1 unit of time. And that equals 2.99793 times 10 to the 10th centimeters per second. There are some uncertainties with respect to other conversion factors, both as to the accuracy of the experimental values from which they have to be calculated, and as to whether all of the minor factors that enter into the theoretical situation have been fully taken into account. Some improvement has been made in both respects since the first edition has been published, and the principal discrepancies that existed in the original findings have been eliminated, or at least greatly minimized. No significant changes were required in the values of the basic natural units, but some of the details of the manner in which these units enter into the determination of the constants and other physical magnitudes have been clarified in the course of extending the development of the theoretical structure. One of the problems in this connection is that of arriving at a decision as to which of the reported measured values should be used in the calculations. Ordinarily, it would be assumed that the more recent results are the more accurate, but an examination of these recent values and the methods by which they have been obtained indicates that this is not necessarily true. Apparently, the consistent values listed in the up-to-date tabulations involve some adjustments of the raw data to conform with current theoretical ideas as to the relations that should exist between the various individual values. For purposes of this present work, the unadjusted data are preferable. The principal question at this point concerns the experimental values of Avogadro's number, as only 3 conversion constants are required for present purposes, and there are no significant differences in the measurements of the quantities that will be used in calculating 2 of these constants. The more recent values reported for Avogadro's number are somewhat lower than those reported earlier, but the correlation with the gravitational constant, which will be discussed shortly, favors some of the earlier results. The value adopted for use in evaluating the conversion constant for mass, 6.024486 times 10 to the 23rd grams per mole, has therefore, gram mole, 6.02486 times 10 to the 23rd per gram mole has been taken from a 1957 tabulation by Cohen, Crow, and Dumond. So that is, Avogadro's number is the amount of atoms of something that weighs, I I believe the amount of the atomic weight of that atom. I'm not exactly sure, but I believe that that's what the number is. You need 6.02 times 10 to the 23rd atoms of oxygen to, or of whatever, silver, to uh, to get to the atomic weight of uh, that element. Uh, I'll have to re-examine that, but I think that's approximately what the number is. So basically, it's, or what that constant is. It's um, the amount of atoms or molecules that you need. So therefore, the units are per gram mole. So if you have a mole is 6.02486 times 10 to the 23rd of atoms. If you have that many atoms of silver, then you have uh, whatever silver's atomic weight is, 76 or something. Silver is atomic number 47. So I guess it's something like 120 or something like that. It would be 120 grams. Um, anyway, in any event, those are Larson's next words, which is a similar synonym for anyway. It should be understood that whenever the results obtained in this work are expressed in the arbitrary units of a conventional system, they are accurate only to the degree of accuracy of the experimental values of the quantities used in determining the conversion constants. Any future change in these values resulting from improvement of experimental techniques will involve a corresponding change in the values calculated from theoretical premises. However, this degree of uncertainty does not apply to any results that are stated in natural units or in conventional terms such as units of atomic number that are equivalent to natural units. As in the first edition, the natural unit of time has been calculated from the Rydberg fundamental frequency. A question has arisen here because this frequency varies with the mass of the emitting atom. The original calculation was based on the value applicable to hydrogen, but this has been questioned as the prevailing opinion regards the vague applicable to infinite mass. I'm sorry, the word is value, regards the value applicable to infinite mass as the fundamental magnitude. A definitive answer to this question will not be available until the theory of the variation in the frequency has been worked out. But in the meantime, a review of the situation indicates that we should stay with the hydrogen value in the interim. From the theoretical viewpoint, it would seem that the unit value would come from an atom of unit magnitude rather than from an infinite number of atoms. Also, even though the difference is small, the value thus derived seems to be more consistent with the general pattern of measured magnitudes than the alternative. From the manner in which the Rydberg frequency appears in the mathematics of radiation, particularly in such simple relations as the Balmer series of spectral lines, it is evident that this frequency is another physical manifestation of a natural unit, similar in this respect to the speed of light. It is customarily expressed in cycles per second on the assumption that it is a function of time only. From the explanation previously given, it is apparent that the frequency of radiation is actually a velocity. So it's not cycles per second, it's a velocity, which is space over time. So it is a distance per time. The cycle is an oscillating motion over a spatial or temporal path. And it is possible to use the cycle as a unit only because that path is constant, and also that path is 1 unit. The true unit, which is 1 unit of space per unit of time, or the inverse of this quantity. This is the equivalent of 1/2 cycle per unit of time, rather than 1 full cycle, as a full cycle involves 1 unit of space in each direction. For present purposes, the measured value of the Rydberg frequency should therefore be expressed as 6.576115 times 10 to the 15th half cycles per second. The natural unit of time is the reciprocal of this figure, or 1.520655 times 10 to the minus 16 seconds. Multiplying the unit of time by the natural unit of speed, which is the speed of light, 2.99 whatever times 10 to the 10 centimeters per second. You multiply that by that 1.52 number, and we obtain the value of the natural unit of space, 4.55816 times 10 to the minus 6 centimeters. That is the measure of the natural unit of space. So that's his derivation there of using the Rydberg frequency. And that is, where you get the speed of light from. And that how the speed of light is the midpoint of the universe. Okay, we will move on in this chapter on constants tomorrow. But thank you for tuning in, and hopefully you'll tune in tomorrow when we continue. Have a great day.